Thank you. Again, I'm David Winters. I'm one of the architects of the data science and engineering team at GoPro. And this talk is really a case study of what we had to do to be able to support deletion of data for big data systems. Something that's very prevalent these days, especially with various privacy laws that have been enacted and will be enabled very soon. So go ahead and get started here. Try to keep us on time. I know we only have about 30 minutes for the talk here. So just real quick background on myself. I've been fortunate to work in Silicon Valley in the Bay Area for actually almost 25 years for a lot of different companies, and it's always really been with data-related systems. E-commerce back-end systems, data warehousing, search index systems, those sorts of things. And so the agenda is actually pretty straightforward. I'm going to talk just a little bit about the GoPro data platform, just so you know the kind of type of data that we have. Then I'll talk a little bit about GDPR and CCPA, which is the California variant of our privacy law that's going to go into effect actually very soon here. And then we'll talk about some of the challenges with the existing big data storage formats, the immutability of them, and then we'll talk about some newer storage systems that we have available, open source projects for big data platforms where you can actually mutate the data. And then finally, I'll talk about an alternative, kind of what we ended up and did at GoPro, so that you don't have to basically rewrite or completely change your infrastructure in your big data platform, but you can still support those delete requests. So with that, I'm going to jump in here, high-level architecture picture of just the GoPro data platform. At this point, I'm not even sure we have many dozens of data sources. Some of the most important ones you'll see, like in the upper left-hand corner, the GoPro cameras. So we do get a lot of really wonderful, rich analytical data from our devices. So we can really learn how people are using the product. We can improve it, even find bugs in various hardware and third-party manufactured OEM parts and those sorts of things. On the bottom of the diagram, you'll see the various icons for quick and our GoPro capture, mobile apps and desktop apps. A lot of people don't know that, but GoPro actually creates a lot of great software. It's actually all free, and you actually don't even have to use a GoPro camera. You can actually use it with your iPhone or your Android device, do auto edits, and then manual edits. The GoPro Quick application is excellent for that. We also get really rich analytical data from those applications, and it, again, can improve the systems, the applications through that. On the top there, we do get a ton of social media data these days. GoPro, we're very fortunate, is a very well-respected brand. We do a lot of sentiment analysis and try to understand exactly what is the feedback on our products and various promotions. And then on the right side is more the egress. We're pulling insights out. We use a lot of Spark notebooks for visualizations, Plotly. There's, of course, the marketers always love the CRM workflows and systems that send advertisements and through email and mobile push messages and obviously user segmentation, those sorts of things. A little bit more specifics here, but I kind of covered that in the last slide, so I'm going to actually move through this one so we can jump into the GDPR basics. I'm going to, you know how it is, there's always these legal disclaimers. I do want to make sure everyone knows that I'm not advising anyone on GDPR or CCPA, practices or anything. And the things I talk about here are really for general background purposes. It's not necessarily, doesn't necessarily reflect business practices that we use. And you should obviously consult with your legal counsel for anything related to data privacy laws. They are very challenging to interpret at times. So what is GDPR and CCPA? So these are two laws that one went into effect last year, May 25th, 2018, the General Data Protection Regulation. It's technically an EU law. But pretty much if you do any business with an individual or a consumer who lives within the European Union or a country within the European Union, it pulls your company into it pretty much. CCPA, the California Consumer Privacy Act, is California's version of it. Very similar, but there are some differences. Obviously, once again, you should really consult with the legal counsel for those things. But the important parts are this. There are various rights that consumers and individuals have. Two of them, which you hear a lot about, is a subject access request, which is a user can go to a company, go to an organization and say, hey, I want to know what you know about me. And you have to provide all of the records. There's also an erasure request, which is, again, a consumer comes in and says, hey, I want you to delete all my data. There's various means and how they can, communicate with you and contact you and, legal timelines and so forth, but that's the basic gist of it. And the challenging one is really the erasure request oftentimes, because these big data platforms that almost every corporation has these days, they were really built so the data is immutable. It's not really easily deleted. So we're going to talk about that next. So we're definitely not going to go through every single Spark or Hive file format. There's many dozens of those, but I'm going to talk about 3 popular ones here. Avro, which is a row-oriented storage format, and then Parquet and ORC, which are columnar storage formats. So when you start thinking about Avro, at least it's row-oriented, so if you were trying to delete rows, it's just, a block of bytes there, essentially, that you would need to, pull out of that stream of bytes. The columnar ones, Parquet and ORC, are much more challenging. They store their data by column values, so that would mean if you have, say, 100 columns or so in your table, you're going to have to pull bytes out in 100 different places or so in each file just to delete a single record. So that definitely is problematic. And then all of these file formats, through the years, they've been around a while. They've been utilizing lots of performance enhancements. So they use a lot of compression. They're actually very intelligent about their compression. Sometimes it's block level, sometimes it's page level. They now have index structures to, again, improve range scans and so forth. They have page level statistics so that a lot of the various computations you try to do and group by statements and so forth are very quick. But what it really comes down to is those files, they kind of stand on their own, and you can't just pull out, a few bytes here or there. You have to rewrite the whole file. So it definitely makes it much more challenging to try to do updates. And then when you take a look at the underlying storage systems that they use, historically, or originally, they used HDFS, the Hadoop Distributed File System. Now that's sort of a meta file system. It has these huge blocks, generally anywhere from 128 megabytes to 256 megabytes, sometimes even larger. And that makes it, again, even harder yet. If you're trying to just change just a few rows here or there, you're writing some pretty big blocks of data over again. And then a lot of companies the last few years have moved more cloud-oriented. And so that means they're using object stores that are provided by their cloud provider. Amazon provides S3, which is obviously used by a lot of companies. That's even more challenging. There really are no blocks, at least externally to the end developer, because it's a black box. Internally, there may be. And so what that means is you truly do have to rewrite the whole file if you want to make just a single small update. So the takeaway, again, we already talked about the data privacy laws. They obviously require us to be able to mutate that data. And now we take a look at the big data file formats. They're designed to be immutable. And so the conclusion is, obviously, you need to have a mutable big data storage system. The good news is that the big data community has been thinking about this for a long time. And so there are several options available these days. Some of the reasons weren't even always related to these privacy deletion requests. If you did any streaming ingestion of data, trying to do that with these big data infrastructures are very challenging. You oftentimes end up with many small files, which is definitely going to kill your performance over time. If you have things like slow-changing dimension tables, where you have a reasonably good-sized table and occasionally a few rows change, you don't want to really have to drop the whole table and reload it every single time. It may work at first, but as your data continues to grow, you're going to run into some bigger challenges. So again, a immutable data storage format would help here. Data restatement, and this is basically the perfect case for slow arriving data. A great example of this would be social networks. You may have made an announcement your company did on say, a social network platform, and yeah, you may get 90% of your data within the first, say, 24 to 72 hours, but it may take up to a month, sometimes even 2 months, until you get that final, we'll say that kind of, that long tail there, that final 10% or so of data. And oftentimes that data is your very valuable data. It won't just be instinctual gut reactions to some information you sent out there. Maybe it's related to a new product you have. It may actually be data that comes in later from end users that actually have bought the product and have some very valuable feedback. So you want to incorporate that data. And once again, you don't want to have to drop all the data again and then reload it just to get an update. We've already talked about the privacy cleanups, obviously needing to be able to mutate the data. And then there's also compactions. I talked earlier about the small file problem, which is a real problem with big data. It's going to kill your scan speed, lots of I/O, reading these small files, you don't want that. So you would like the ability to also be able to compact those small files into larger files. And once again, a mutable data format is going to help you a lot more with that. Several recent open source projects that support mutations on data storage. Apache Hoodie, which came from Uber, has been supported a lot by Confluent recently, the company behind Kafka. It's been around probably about 3 years, pretty mature product, works with both Hive and Spark. Databricks Delta Lake, which started off as a proprietary feature from the Databricks Spark service. And then I think it was about 6 months ago they open sourced it. It's a partial open sourcing right now. They haven't put all their features in it, but it's definitely very promising. And we'll talk about it a little bit more in a few seconds here. And then there's the Apache Hive ACID transaction tables, which has been around about 4 years. So it's very mature, but it is really built pretty much just for Hive, not really for Spark so far. And then you have some newcomers like Apache Iceberg, which is from Netflix. And it has taken more of an approach more around query planning and execution right now, but they're actually working on mutation support also. So when you take a look at this, and I'm not going to go through all these tables are pretty large, but it kind of lays out a lot of the main features here. And I actually color-coded like green for things that were good for our use case, and then red, things that were basically bad for us, and the black is kind of neutral, doesn't really have an effect on us. I'm going to jump to the summary here. What it really came down to is all of our requirements were not met by any of these open source projects. And our requirements were, at the top there. We wanted to support, obviously, for some updates and some deletes. It could be through an API, it could be through a Java API, a Scala API, or it could be through DML, which would be preferred, which means you could do update statements and delete statements directly in SQL. That would definitely be a great benefit for our data scientists, which are going to be more prone to using SQL and a little bit less to using APIs. Parquet file support, since about 90% of our data is stored in that columnar format. I have Spark 2.4 down there, but we're basically just saying a modern version of Spark, a recent version of Spark. Manual or automatic compactions, once again, definitely a problem with all big data platforms. You want to be able to compact those small files into nice large files to improve your scan speed. I kind of already talked about that. Nice to have the DML support. And then the concerns, and this actually became some of the largest reasons for why we were not able to move to any of the existing open source projects, was the data migration time. Oftentimes there was no migration path, so there is additional metadata that's stored, obviously, to be able to track these mutations. Sometimes it's stored directly in the data files. Hoodie does that with storing it directly in the Parquet files. Definitely problematic because you have to rewrite all the Parquet files. Some of the other systems just have other outside data sources. They either use key value stores or relational databases, or even the file system sometimes in JSON files. But again, all that metadata has to be extracted, has to be populated. You need some way to migrate the data. And so we ran into either there was no data migration path, really, at least, or we'd have to create one, or it was too time consuming, or it just flat out failed. And then there's the insert and query performance overhead. Obviously, there's overhead here. You can't just go and read from the files any longer. There's going to be some reconciliation you have to do with some external metadata. So since all of our requirements weren't met by any of these open source projects, and we also didn't want to have to completely change all the infrastructure for our data platform, we decided to develop our own data cleaner tool, which would allow us to basically do these deletions and keep our same infrastructure as it is. So we'll talk about what we developed. So our requirements were almost the same as I talked about before for our data cleaner project, but they were also just slightly different. In some cases, they were a little bit narrower. In some cases, they're broader. I'll just kind of go through them. So we decided after we took a look at things that we wanted to support more than just Parquet files. We do have about 90% of our data in Parquet. We do support some other formats. So we definitely wanted to be able to do that. We also wanted to support all data types, all table types. We use pretty much everything under the sun. We have a mixture of, we have some Spark tables, we have some Hive tables, we have partitioned, we have non-partitioned, we have external tables, we have managed tables. So we need to be able to support all of them. We decided that as much as we'd love to have update support, we could live with delete only at this point. And then we did want a modern version of Spark. We were in Spark 2.4, so we went with that. And then the bonus was if we could have the ability to at least do manual compactions would be fantastic. So some other things that kind of crept into our requirements and our thinking as we started to do some proof of concept work and some early development prototyping is we decided pretty quickly we certainly didn't want to have to maintain all sorts of code for every single Hive file format. That would, for one thing, it would just be redundant. There are already platforms such as Spark that already do that. And so that made our decision to go the direction of Spark SQL for all of our operations. Now, when you look at Spark SQL, there was only one way to really overwrite data. There is an insert overwrite command. And you can do it at the partition or the table level. So that kind of knocks that off our list, where we can support both partition tables and non-partitioned tables. It also worked after we did some tests, and you did have to get just the right Spark version because there have been some JIRAs that were fixed in time. But it could also work for both managed and external tables. And then the best yet, it worked for both Hive and Spark tables. So this is just a very simple to give folks, especially folks that are familiar with Spark and Spark SQL, just a very simple example of what you can do with Spark SQL to basically implement a delete using an insert overwrite. So in this case, I have a very simple employee table. I'm using Parquet. Again, what we ended up in developed, you can actually use anything you want, but this example uses Parquet. I use snappy compression. I decided to partition this table by a date and an hour columns. And then it's an external table since I'm supplying the location. Insert some data here, my childhood favorite, the Flintstones characters. And then here's what you can do and this is actually working code. You can actually copy and paste it into a notebook or into a Spark shell. This is how you can use an insert overwrite to implement a delete in Spark. So we start off here, we have to fetch the partition, so you do have to do it one partition at a time. So in this particular case, I'm fetching our partition for the date of 2018, 08, 02, and the hour, the midnight hour, essentially 00. And then there's some debug statements in there, but I take that partition. The next thing I want to do is you have to filter out the rows that you wish to delete. In this case, I'm filtering out any user that is basically Fred Flintstone's email address or this guy Ted's email address. And now I have my updated partition. Now this is where Spark, a nuance to Spark. Spark is intelligent and it knows it doesn't want you to just pull a partition from one of its tables and then write it right back, because it knows you could end up in an inconsistent state if the task fails. And so what Spark does here is they force you to basically write it into a temporary table, which is not a bad thing. It's not a bad thing for one thing if your operation or one of your tasks fails halfway through, you don't end up in an inconsistent state and you can rerun the operation. But it's also good because it gives us the ability in the future to archive data as we're deleting it. Because even though we're deleting this data and we do want it to go away forever, we also do want to be very careful with this data. And we want to make sure that there's not a mistake made. And so in this case, a standard process for a lot of organizations can be you do your deletion, then you verify the deletion is correct, and then you drop your archives. And so in this particular case, we're not going quite that full route to the archiving, because again, I want to make it a simple example. But we write the temporary table. After we write the temporary table, we're going to read that back essentially into memory. And we actually have to use, for this very last insert and overwrite, the cleaned up partition, that comment there, you actually have to use Spark SQL itself to do the insert overwrite. It's just a nuance to Spark SQL. There's not a Scala or a Java API to do it. There's lots of JIRAs filed on it. But so you do have to kind of shift gears a little bit. We have to go full Spark SQL at the end there and do the insert overwrite. But it actually works. So what we did next was, obviously that's a very hard-coded example. That certainly isn't going to work for the huge number of tables that we have. And so this is a class diagram of what we ended up and came up with. So we created a facade at the very top there, a user data cleaner class. And the idea for this was its responsibility is to delete all user data. You give it a list. In this particular example, on the right-hand side, you can see it's given an emails.csv file. So that's going to be a list of email addresses. It could be other IDs also. Obviously, email address is not the only way to identify a user, but this particular case, in a use case that's pretty popular, is email address. You also give it, on the left-hand side, you'll see a tables configuration file. In our architecture, it can either be a JSON file or a type-safe config file. And that describes all the tables. So you list out all your tables, and we're going to take a look at an example of that next. And then there's a series of delegations that occur. The user data cleaner instantiates a Hive table cleaner. The Hive table cleaner, depending on the type of the table, if it's a partition table, it will instantiate a Hive table partition cleaner. If it's non-partitioned or just a good old straight table, it's going to instantiate the Hive non-partition table cleaner. The nice thing is we learned after we did this was as we were doing the deletion, it was a great opportunity to do the compaction. So we could repartition the table at the same time. So let's say we had a table that would end up with every single partition having tens of thousands of files. At that point, we could take a look. We could analyze the size of the data, and we could basically repartition it. So maybe make it 1,000 different files. And so that's what that Hive table repartitioner is at the bottom. Is it's essentially a delete with a null filter. It just filters out no rows, and it just rewrites the files in a nice compacted format. We also use a lot of HBase at GoPro, and so we wanted the user data cleaner to handle all big data in this particular case, so it also cleans HBase. HBase is a transactional system, so deletes are natively supported, so that's very easy. Here's just a few examples of some of the JSON configuration for some of the tables. This is, like I said, a JSON version of it. You can see we define the type, Hive in this particular case, the name of the table, the database. Some things like partition columns, that's something we could get from the Hive meta store. It will be a feature that we'll work on in the future to just reduce the configuration. You can define your ID column, which is how you're going to identify the row that needs to be deleted. We later added actually support for compound keys also. And then we actually even support different types in encoding. So you can do normalization of email addresses, trimming off white space, lowering it to lowercase text, and those sorts of things. And then we also have a type-safe config version. In this particular case, you can see it also supports the HBase tables, and also has some Hive tables listed here. So kind of the summary is, what we developed was we developed a cleaning and repartitioning framework on top of the existing big data infrastructures that everybody uses today. It is based on Spark. It did use Spark SQL, the insert overwrite in particular, to implement that deletion. It's configuration driven, so we are constantly, new tables are being added to our platform nonstop. You just change configuration to do that. Backups are supported so that we can first verify that a deletion was successful, and we have a rollback strategy in place if we have to. It also, and I didn't talk too much about it, but we've added some further feature support for relationships between tables. I spoke a little bit about how you could delete by email address. You can also delete by other IDs, internal IDs, and so forth, do translations between them. Which makes it a lot easier to do deletions across a wide variety of tables. It's scalable because it uses Spark. And then a bonus, we do have a repartitioning tool that comes with it. And then we're currently working on open sourcing the project. Hopefully that will be out in the next few months. So definitely check our GitHub, github.com/GoPro. And it should be out there hopefully very, very soon. So thank you, and I will, I think we're in pretty good time. I'll open it up for questions.
Yeah, definitely. Great presentation, thank you. How long did it take you to roll it out?
Well, the full development, it took us probably from initial concept, and so there were several revisions of it. But the first version we were able to complete in about 3 months. It was very manual intensive, that version, and you did have to do manual translations between IDs that you wanted to delete. And then it was about 3 months later, so probably total about 6 months to the point that we're at now.
Thank you. That's super impressive, especially given that it's configuration driven.
Yeah, I mean, it's we've always attempted to be as reusable as possible. And we do have a small, the data science and engineering team is pretty small at GoPro, so we don't want to spend a lot of time. We'll take the time to invest in the infrastructure so the next time is a lot faster.
Any other questions?
Do you have a use case that you need to clean up analytic data? For example, a user spent $5 on a product and you have an analytic data saying the sum of all the user purchased product is that. When the GDPR come, and not only you need to clean up the user's data, you also probably need to consider the analytic data as well, right?
You're absolutely right, and this does also clean up. So first of all, it is a very generic table cleaner. So any table that you have in Hive or in Spark, you can clean up. And yes, most of our tables are analytical tables. So we have transactional tables. We have analytical tables, which come from devices and from like software. And then we have what we call aggregated tables on top of those. And those grow very fast. And so basically that's why it had to be configuration driven, because after that first version, which took about 3 months to develop, we realized right away it was going to be a bit of a maintenance nightmare to have to maintain that. And so yeah, there's constantly new analytical tables that are being added and that we're deleting.
Anyone else? All right.
Cool.
Thank you, David.
Thanks, everyone.